Welcome. Today we're going to talk about inverse of relations. An inverse of a relation or a function can be thought of as an undoing. If a function does something, the inverse undoes it. Recall from a previous course that an inverse takes point xy and maps it into its image point yx. For every point xy on the relation, there is a point yx on the inverse. So our mapping notation that we can use is x comma y maps into yx. So as a consequence, the relation will be reflected about the identity line y is equal to x. And my identity line y is equal to x is this one right here. Y is equal to x. That's the equation of this dotted line. This line is called the identity line. So in my function, I'm going to note my points. Pardon me, that was definitely wrong. This point here is -2, 3. This point is 0, 0. This point is 2, 1. And this point is 4, 1. Now, I'm just going to graph the inverse of this function, or this relation, I'm going to call it for now. So point -2, 3 will map into 3, -2. So simply, I'm going to give this a name A, just for clarification. A will map into the inverse. And if I call this point B, well, point 0, 0, I'm going to switch the x's and y's. It will map into point 0, 0. C is 2, 1. This will map into 1, 2. So this is C inverse. And D is 4, 1, and it maps into 1, 4. So going from A to B inverse, pardon me, that needs a ruler here that I don't have. Going from A inverse to B inverse, to C inverse to D inverse. This is my function. And if you tilt, I encourage you to tilt your screen, tilt it 45 degrees counterclockwise, and you'll recognize that this is actually, function is reflected about the identity line. So if we want to call this one f, this one would be f inverse. But let's be careful. We need to be very, very careful that I don't call it the inverse of function, because the inverse is not necessarily a function. Speaking of which, that's a great transition. Let's talk specifically about functions. A function f will have an inverse. However, that inverse may or may not be a function. If the function f has an inverse that is a function, then it's called an inverse function and denoted by f inverse. Getting back to my picture, let's consider the green graph. Is the inverse a function? No. The inverse is not a green function because point C inverse and D inverse will fail the horizontal, or will fail the vertical line test. So the inverse is not a function, which is kind of bad. So let's look at this a little bit. Consider the function f of x is equal to x squared. So this is f of x is equal to x squared. Without question, this is a function. That's why we studied it all last year, because it was a quadratic function. A function, each x corresponds to exactly one y. And we do this to make sure that it passes the vertical line test. My apologies. We have the vertical line test to ensure that each x maps into exactly one y. Because if an x maps into two y's, it is not a function. However, f has an inverse that is not a function. Therefore, we may have to restrict the domain to ensure that the inverse of f is a function, f inverse. Now, this vocabulary is kind of getting, I'm trying to stumble on vocabulary here, so I'm just going to maybe take it from a more pragmatic approach. Do you see my parabola? My parabola is a function. Now, you're going to have to trust me. I'm going to graph the inverse very quickly for you here. And when I graph the inverse, this is problematic. This is problematic because my inverse of f is not a function. How do I know my inverse is not a function? Well, I draw this vertical line and it fails the vertical line. That is for the x value 4, there's 2 y values. So f is a function, but the inverse of f is not a function. So I can't call it an inverse function. It's just simply an inverse. Additionally, a function has an inverse function f to the negative 1 if each element of the range, each y, corresponds to exactly one x value. So we test the original function with the horizontal line test to ensure that the inverse is a function. If a function passes the vertical line test, and if a function passes the horizontal line test, it is said to be one-to-one. That is, each x maps into only one y, and each y maps back into only one x. This is a one-to-one function. If a function f is one-to-one, then the inverse of f will also be a function, and we'll call it f inverse. To put it simply, the function f will have an inverse function if and only if f is one-to-one, passes the vertical line test. So if and only if is kind of an important math statement. So if f is a one-to-one function, then it will have an inverse, and if f has an inverse, then it must be a one-to-one function. So let's look at this. Consider the graph f of x is equal to x squared minus 2. Is the inverse a function? No, the inverse is not a function. Why? Because f of x f of x is not 1, 2, 1. That is, does it pass the vertical line test? F, yeah, check. Does it pass the horizontal line test? Well, you can draw a horizontal line. What we see is that there's 2 x values corresponding to 2 y values, so it fails the horizontal line test. So we can say this function is not one-to-one, and therefore it will not have an inverse function. It will have an inverse relation. However, let us graph that inverse relation. Just for reference sake, I am just going to do this. There's my identity line. I'm going to make little arrows at the end because I believe there's little arrows at the end of my graph. That's implied. Now, to graph my inverse relation, I'm just going to simply take every point xy and I'm going to graph it into point yx, or reflect it about the identity line. I'm going to start off with taking this point, this point, this point, this point, and this point. I'm taking these points because they have integer values. Easy to see on the graph. I'm going to start off with negative 2, 2. Well, negative 2, 2 turns into 2, negative 2, and will be posted right there, or transformed there. My next point is negative 1, negative 1. If I switch the negative 1s, if I switch the x and y's, it remains stationary. this point down here is 0, -2, which if you switch the x and y's as the mapping notation indicates, you'll end up with point -2, 0. This point right here is 1, -1. So if you switch the x's and y's, you'll end up with -1, 1. Last but not least, 2, 2. Wouldn't you know it? There it is. So every point of our function that exists on the identity line will remain the same. And then there's my inverse. All right, team. This is a lot of fun. Now let's describe how the domain of f of x can be restricted so that the inverse is a function. I think that's fairly straightforward. We have to be creative about it. So how can I cut my parabola, it's indeed a parabola, so that it passes both the vertical and horizontal line test? Well, there's many ways, but I think one way that makes the most sense is that you actually cut it in half at the vertex and only keep one arm. And in this case, I'm just going to say the domain, so describe how the domain of the function can be restricted so that the inverse of f is a function. I'm just going to say keep one arm of parabola. So that would be in words, and I would just define my domain of my original function f to go from 0 to infinity. And essentially what that would do is that would keep this arm. And if you're keeping that arm and you only transform that arm, your inverse function would transform like that. What you see is both the orange, which is f of x, and the green, which is the inverse of f, are both functions. And they are both functions because your original function f was 1 to 1.